Hey, everybody, welcome back. Today is our last lesson of the shortened week, and it's on strengths of acids and bases. So I thought to start off today's lesson, I would share with you the quality music that I used to listen to when I was your age. So this song is called Acid Rock by a band called Rhythm Device, and we're just going to play 30 seconds. And I just want you to appreciate the quality of the music when I was your age and how much it has changed. So enjoy. Oh, wrong one. Let's try that again. There we go.
There was a time that rock and roll was easy, but now it's clean and heavy.
Okay, so I don't think I have to ask you if you think music has improved in the last 30 years. Yeah, I think so. That was pretty brutal. Anyway, I was just searching for a song that had the title Acid in it, and that's what came up from 1989. Believe it or not, in 1989, I would have been about early 20s. That's giving you a hint as to how old I actually am. Holy smokes. Okay, so today we're going to look at strong and weak acids, strong and weak bases. Again, it's a pretty short, straightforward lesson. This week's been kind of nice for you guys. Nothing too heavy. So let's take a look. We've got two beakers here, and the question is, which beaker contains a strong acid? Which beaker contains a weak acid? So what you're looking at here is, if you can see on the legend, this one, the black is the H plus and the red is Cl minus. So we've got some H plus and Cl minus, and it looks like it is 4 H plus and 4 Cl minus. Let's try that again. I'm not counting. 5 and 5. Okay. And in beaker number 2, we also have some H plus and some HCO3 minus and some H2CO3. Okay, and we have one of those, and 4. All right, so the one that stays together is called undissociated acid. In other words, it has not ionized or reacted. So if you look at the ratio here, we've got 4 to 1. So 4 of them that have done nothing and 1 of them that has reacted. So another way to look at that ratio is 1 out of 5 or 20% ionized. And this one, 5 out of 5 have reacted or 100% ionized. So now can you answer the question, which beaker contains the strong acid, which contains the weak acid? And if you guessed strong because 100% ionized, and weak because only 20% ionized, you would be correct. So that's strong and weak in a nutshell. Here's some examples of common household acids and bases. And you'll notice that most of the acids are foods and most of the bases are cleaners. So we eat a lot of foods, we use a lot of foods around the house in the kitchen, and then we clean up our food spills with bases. So acidic foods, basic cleaners. As a general rule, there's certainly exceptions to that. Okay. This is a review from earlier in the unit, properties of acids and bases. So we've gone over this already and you filled it in your notes. So just going to move past that and get into this. Okay, so I've alluded to this before. A lot of the stuff we're going to talk about today, you've kind of seen and heard bits and pieces of. So the definition of a strong acid is any substance that reacts completely. By completely, we say greater than 99% with water to form hydronium ions. And if we want to add our little H plus in there to show the transfer of the proton. So the acid gives the proton to water, making hydronium, and there's what's left of our acid. And if we started with 2.4 mole per liter at greater than 99%, we would get all of that as our product, 2.4 mole per liter. Okay, earlier on in the unit, I asked you to add the 3 strong acids to the 3 that you already have in your notes. So this is on your periodic table on the back. So this data table contains all 6 of the strong acids when you add those 3. Okay, so for high school chemistry, we only look at 6 substances that are considered strong acids. Okay, that's it. 6 strong acids. So you can remember them if you want, memorize them, or always have this table available to look them up. Those are the only 6. Everything else is weak. All right, and we've talked about those before as well. So let's get into this. Weak acids react incompletely with water to form few hydronium ions. So the rule is generally less than 50% reaction. So this is a generic acid. It's got a proton to donate and it's got an anion in it. The anion could be anything. So the H plus is transferred to water to make hydronium, and here's what's left of the acid. So we call it the acid anion, or what's left over from the acid. Here's a real example. This one is acetic acid, or what you guys commonly know as vinegar. Vinegar is considered a weak acid because it's less than 50%, and off the top of my head, I feel like it's around, let's get rid of less than, I think it's approximately 5% acetic acid. So not a lot of it donates its protons to water to make hydronium. So let's say we started with our 2.4 mole per liter and only 5% of 2.4 would be 0.12 moles per liter. So you can see you get a lot less product when only a small amount of the acid reacts, 5% of it going forward. 2.4 becomes 1.2, and that's why the pH, which is a measure of the concentration of hydronium, is usually greater than 2. So often you'll see 3, 4, 5 as the pH for weak acids. That is dependent upon the concentration, but also the percentage of reaction. And strong acids, you get 100%. So a strong acid often has a pH of 0 or 1 or -1 for strong acids. Not always, because if it's a really low concentration to start with, then you don't have a lot of hydronium that you can make. But those are pretty common pHs for strong acids. -1, 0, +1. Okay, moving on. It's very slow today. Okay, bases. So strong bases are any soluble ionic hydroxide. And the reason is they dissociate 100%. So they all start with an ionic metal and a hydroxide. It dissociates 100%. So we get our metal ion, and this is what we're after, our hydroxide. If we start with 2.4 mole per liter, we're going to get 2.4 mole per liter of hydroxide. So strong bases will have pHs usually of 12, 13, 14, 15, somewhere up on that high end because of the 100% dissociation. So the example there is NaOH. Any of those metals, especially group 1. Group 1 is all high solubility. So for example, lithium hydroxide dissociates 100% into lithium ions and hydroxide ions. So all the group 1 metals tend to do that, and some of the group 2s. Hey, we're just rolling along. Okay, weak bases. So just like weak acids, these partially ionize or react with water. I shouldn't say ionize, partially react with water to produce hydroxide ions. And they are always less than 50, and they're often less than 5. So B can be any base they can be both a molecule or an ion. Usually they're ions. Those are the ones that we see most often. This is an example of a molecule. And remember that I said that base will take the H plus from the water. If water loses its H plus, it becomes hydroxide, and that's how we get the basic properties. And then you have a cation left over. A second example, if we went with something like SO3 2 minus, would also be a base that can take a proton from water less than 50%, so partial reaction to make our hydroxide, and this one would be HSO3 minus. So we did these reactions yesterday. We just didn't worry about percentage. So less than 50%. So again, if we started with 2.4 mole per liter, you're going to get way less than that. Ammonia, I can't remember off the top of my head. Let's say it's 10% reaction. It's not, but we'll just use that number. So you get 0.24 mole per liter, significantly less than what we started with our 2.4. And there are lots of bases that are less than 1%. So weak bases will have pHs of 8, 9, 10, maybe up in that 11 range for a pH. Depends on concentration and percent reaction, but they're definitely closer to 7 compared to the strong bases. Okay, this chart is a nice summary of all of the properties, empirical properties that you can observe. So you can measure the pHs. You can measure conductivity. Strong acids and strong bases are high conductivity. Weak acids and weak bases are low because they have only a small percentage of ions, less than 50% ions. So they have lower conductivity, and they have slower reaction rates because they have less ions to react. And we already talked about the theory explaining why that is with complete and partial reactions from strong to weak. Okay, so the last part of this lesson is a little bit of a thinking exercise. So it's visualizing the difference between all of these. So using HX, so that's going to be our acid, show the difference between strong and weak acid and concentrated and dilute in 4 beakers. So I will draw out 4 beakers. I fear I've not made these large enough. Okay, HX, so strong and weak. So in a strong acid, what percentage of them will break apart into H plus and X minus? That should be an H, darn it. And let's put a 4th one in there, H plus X minus. So we would call that one 4 out of 4 reacted, or 100%. So is that strong or weak if 100% of them reacted? Okay, what would a weak acid do? What percentage of them would react? Less than 50. So let's go with 1 reacts and 3 don't. 3 stay together. Okay, so that's 1 out of 4, 25% weak. Okay, so that's our strong and weak. Now we also have to add in concentrated and dilute. And those are terms that we use when we're comparing. So I'm going to call this one concentrated, and I'm going to call this one concentrated. We're going to say that they are 4 molecules per liter. 4 molecules or 4 moles per liter. Okay. So now I want to do a strong dilute acid. So dilute means it's less concentrated. So we are going to go with 1 mole per liter. Because it's strong, it's 100%. 100% of it ionizes, but it's only 1 molecule per liter, 1 mole per liter. So it is still a strong acid, but it is dilute. So if you compare both strong acids, both 100%, but concentrated, 4 moles per liter, dilute, 1 mole per liter. So that's our difference. Now I want you guys to draw what will a weak dilute acid look like. It's weak and dilute using our HX model. If we were going to go with 1 mole per liter or 1 molecule per liter, what would we do with that 1 molecule? Leave it together. Because less than 50%, less than 10, less than 5%, a small amount of them ionize. So that looks like a weak acid. That looks like a strong acid. These are both dilute, and these two are concentrated. Okay, hopefully that makes sense. This is a common Chem 30 question as well. We test the same thing in Chem 30. Okay, so now we're going to do the exact same thing, but it's going to be bases. Strong and weak base, concentrated and dilute. So this is where you are going to pause the video and try and answer this one on your own in your notes using the XOH and X minus. See if you can figure this out. If you have no idea, then you can just continue watching. If you think you got it, pause and try it. Okay, so XOH represents strong ionic hydroxides. So I'm going to call this one strong. And let's put strong. No, let's follow our same pattern as before. So we'll put the strongs there. And we'll go concentrated and dilute. Okay, so strong base concentrated would be our strong is an X plus and an OH minus. It's 100% dissociated. And again, we'll go with 4 molecules just to keep it the same as the acid. So that is 4 molecules in our liter, 4 mole per liter. A mole isn't really a molecule, but we're just keeping it simple for this model. Now, our strong acid is 100%. So again, this is strong base, 100%, but it's dilute, so only 1 molecule per liter. Okay, so this one is 4 times more concentrated than the dilute. Now, a weak base is usually something that reacts with water. So X minus can react with water to take an H plus, so it would form HX and OH minus. So that's if it reacts. So our weak base, how many of them will do that? A weak base that is concentrated. So if it's weak, it is less than 50% of them will react with water. So I'm only going to have one of them react and make HX and OH minus, and the other 3 will not react with water because it's less than 50% and it's concentrated. So just to review that one, it's a little trickier. One of the molecules, one of these reacted and made HX and OH minus. 3 of them did not. They just stayed in their original form because they're weak. Less than 50% react. However, it is concentrated. We did start off with 4 moles per liter of X minus, our weak base. Only one of the 4 reacted. Now we go to our weak and dilute. So I think you can all predict what this one's going to look like. Weak, less than 50%. Dilute, we're only going to do 1 molecule. What will that 1 molecule look like? Will it be X minus or will it be HX and OH minus? Correct answer. Actually, I can erase that instead. x minus, because that is the weak base in its original form, because very small percentage of it will react. Okay, so hopefully that makes sense to you guys. That's sort of the theoretical way of interpreting these using a diagram. And because it is diluted, it's also one molecule in the liter. Okay, by the way, all of these things should be drawn as solutions, aqueous. Same with our previous example for the acids. These things are all aqueous in solution. Okay, awesome. I think that takes us to the end. Look at that. A few questions to practice in your textbook, numbers 1, 2, 3, 5, 6, and 12. And there is a short quiz and assignment. Oh my gosh, this is messy. Based on the last 3 days, but it's going to be short. Tomorrow is grad, so no classes tomorrow. Short quiz and assignment that'll be linked to this lesson as well. Okay, have a good afternoon, and I will see you guys after the long weekend when we finish off this chapter. Okay, take care.